Welcome. In this next session, we'll be talking about imaging AI and some applicable parts of DICOM and IHE. I'm Kevin O'Donnell. By way of disclosures, I work for Canon Medical, but none of this talk is vendor specific since we'll be talking about open standards. So I'd like to start with this slide from Brad, which is based on our imaging AI white paper. It highlights the many potential applications of AI throughout medical imaging. While much of the attention has been on step 5, many of the tasks in data handling are ripe for automation or assistance. From ordering and scheduling through image acquisitions, all the way down to doing analysis of population health and departmental operations. As a side note, I'll note that the clip art in step 9 seems to be a picture of a department store, which I guess we'll assume is where hospitals go to buy departments. I'll tell you now, the radiology department might be one of the more expensive items, but it really does go with everything. I'm a firm believer that we're going to see as much AI in all these other areas as we do in image analysis, but for now, we're going to focus on where the recent attention has been, which is AI performing inferences on images. Now, there's a reason for that attention. AI breathes data, as input, as output, lots of it for training. So where does that lead us? Well, if we think like Willie Sutton, two of the largest pools of data in the healthcare enterprise are the EHR and the PACS VNA. And thanks to the foresight of pioneers in the field, we have the DICOM standard. AI has benefited tremendously from having images in a standard format going back to the early 90s. Places like Hopkins, Mayo, the Cleveland Clinic have literally billions of DICOM images stored, amounting to petabytes of data. And not just stored, managed and indexed. Imaging has been using a standardized digital workflow for decades now. Standardized format, it's readable across hospitals. They are persistent objects that can be indexed, transferred, used for training, etc. This differs a little bit from HL7 messaging, which is the standard that's been used for the EHR. The messages are not inherently persistent, and implementation has been idiosyncratic. Fortunately, the development of the HL7 FHIR standard is coming along strongly. They've made great strides over the last 12 years. Deployments have begun, and as it matures, it will be a big game changer. It touches so many care processes. It'll provide entry points for so many AI tools. But for now, let's get back to imaging. As a high value add service within healthcare, it's also got a lot of financial and technical attention to really deal with some of the implementation issues. Speaking of which, I'd like to go to this other slide of Brad's, which asks, how does AI fit? Imaging involves multiple steps in the imaging workflow and multiple different systems. And so the question is, how do we weave an AI model into the mix? AI isn't something where you just turn on the switch and everything does AI stuff. There are some AI applications that are embedded. Things like AI-driven image reconstruction, it's embedded in the product. And so there isn't a lot of integration needed. But for something like image reporting, there are multiple systems at play and a lot more integration is involved. So let's have a look at an overview of the current IHE AI profiles. I'll assume you've had a brief intro on IHE. Basically, it's a meta standard that writes implementation guides for how to use other existing standards to address particular use cases. And it creates documents we call profiles. So in this case, we'll be talking about the AI results profile, which addresses encoding and displaying the output of the image analysis. We'll be looking at the AI workflow for imaging profile, which essentially coordinates the pre-processing of these AI tasks for imaging studies. We'll look at the IHE prioritization of work lists for reporting, which involves feeding data, including AI triage results and other findings to a work list prioritizer. And then finally, the IHE integrated reporting apps profile, which is about synchronizing data and context, including ad hoc AI tools during reporting. So starting with the AIR profile, the target systems for this are the AI analysis software that creates the AI results, the image displays that present them, say, to a radiologist during the reporting process, and the PACS that stores them in between those two. So we're trying to standardize the storage and the display of these AI results that are used for image interpretation. The method is we defined a set of result primitives, which we'll talk about in a moment. And then on the creation end, we have encoding requirements for how those are created in a standardized way, spoiler, DICOM based. And then baseline display requirements for how the displays are expected to handle those. Now, before we dive in, it's useful to think in the context of the larger life cycle of an imaging AI application. Let's start with the collection of annotations that your experts are creating to train the AI in the first place. That's a large set. It's going to need to be stored. It's going to need to be managed. So we're looking for a storage format. You're also dealing with the results that are coming out of the AI, that those too will need to get stored there. And those will look very similar to these training annotations because essentially, that's the point of the AI. When we're doing the training annotations, we're showing the AI how to do the task that we're trying to automate. So there's some symmetry there. The task may have been done manually in the past. In fact, it likely was, in which case we will also be referencing past annotations from the clinical record. Since it's in operation, there's the potential for doing corrected annotations. The AI won't always get it right. You don't want the wrong answer going into the patient's record. The clinician will sometimes either reject it outright or put in a correction, which in turn you'll want to be storing and then feeding back into subsequent training to improve the performance of the application. And in most cases, you'll be collecting new data over time to broaden the generalizability of the app. You want it to be able to work for additional modality models, maybe handle new forms of the pathology, spiculated tumors in addition to lobulated tumors, etc. So you're going to need to associate all of those forms of capture together with the images that are underlying them, because all of those are annotations relative to the clinical imaging that was done. And of course, we need to manage the large and evolving collection of information, which means we need to have metadata. So to address this broad life cycle, we're looking for metadata-rich formats that let us put this all together in scalable large storage. The good news is hospitals already have systems to store and manage large collections of images and associated metadata and data. DICOM is happy whether the recorded creator is a human or an algorithm. Now, depending on the sequestering capabilities of your PACS, you won't necessarily be using the same instance of your PACS for both operational purposes and training purposes, but you can basically leverage the technology and the products. So let's talk about the result primitives. AI is output. Ideally, the premise we have is that most of the results can be encoded as either one of these primitives or a combination of primitives. The first flavor is qualitative findings. For example, the breast composition is extremely dense or pneumothorax is present. This can be encoded in DICOM SR using template 1500. We'll come back to that in a few moments. Measurements are obviously going to be huge. They're tedious for the radiologist to do, and if the AI can do them quickly and accurately, then that's a wonderful thing for all concerned. So those sorts of things also fit into TID 1500. Locations, it may have identified, say, a blood clot, and you want to know the coordinates so that the display system can mark that up so that you can potentially track it over time. Again, TID 1500 using the 3D spatial coordinate capability. And then segmentations. Once we've located, say, a lung nodule, we may want to do a surface segmentation to do further estimates of its volume or other characteristics. There are two ways that are likely. The DICOM segmentation IOD is built for capturing exactly these kinds of segmentations. NTID 1500 also supports ROI contours, so essentially outlining the feature of interest on a number on each slice over a group of slices. The profile also discusses the use of heat maps. There's some controversies over whether those are accurate or beneficial or not, but if the app is using them, there's a way to use those. Longitudinal tracking IDs, once you've identified that the tumor in this prior study is the same tumor as the current study, they can be tagged so that you can do longitudinal analysis, etc. Now, we'll jump back for a moment. I gather from Brad that you will have seen DICOM structured reporting objects before, and so are a little familiar with the idea of the content. A template for SR basically outlines a particular form, a particular collection of items to put into a given SR. You can think of them, they're very similar to XML. In fact, there are XML encodings of SRs. Or you could think of them in terms of a linked set of nodes. In this case, you can think of a distance measurement shown here, 37.6 millimeters, which is then linked as inferred from another node, which is the pair of coordinates that led to that measurement, which in turn is selected from a reference to the image that underlies the measurement. Now, these trees can get fairly large and complex. There's an example of one here for a mammo CAD report, and so there's a variety of these contained in DICOM. A bit of a list on the right side here. We've got templates for echocardiography, for mammography, radiation dose, etc. And then there's some general purpose templates like 1500 that are used for capturing the measurements and observations that we've been talking about. If you want to go delve into the standard, the templates are all in DICOM Part 16, and you'll see a lot of tables like this. It may look a little daunting, but if you focus mostly on the concept name column, each row is capturing a particular piece of information. For example, on row 3, we're capturing the target region of this CT scan. And in the value column, you'll often see things like pointers to code lists that you can use to fill in that field. So CID 4030 is a whole bunch of SNOMED anatomy codes that would be appropriate for CT and MR anatomies. For things that are numbers, such as measurements, you'll often see the units described over there. If you prefer working in JSON, Supplement 219 basically describes a complete transcoding method for going back and forth between a JSON representation and a traditional DICOM representation. There's also a number of open source tools that David Clooney has developed and is available on his website. And the basic idea here is you'll see there's a lot of use of aliases, or here called business names. So we can see in the middle of the result there, the finding site is the ascending aorta. Over on the right, we can see that ascending aorta is simply an alias for the SNOMED code for ascending aorta. So it keeps them relatively reasonable, and for people who prefer processing JSON, a little more convenient. The last part of this then is those display behaviors. So the question we were trying to answer here is, how does a display, like an image display workstation when you're doing your reading, become AI ready without having to go out and customize how it does displays for each of the literally hundreds of AI models that are out there? And so again, it comes back to these primitives. We put together a baseline set of display requirements for each primitive. It's permissible to have, and in fact probably encouraged, to have additional or alternate functions that the display can do with these inputs, with these primitive results, that the user can invoke or the system can be configured to use. But we wanted to make sure there was a baseline of basic capabilities so that they would be at least useful from the start. Measurements, for example, need to be presented in the context of the image where they were measured. The system has to be able, if called on, to display locations and the labels that go with those. It should be able to label segments and volumes, overlay parametric maps, which are sometimes used for heat maps. If you're, for example, trying to localize the area that was called out as potentially a pneumothorax, for example. And associate multiple results in a set by that tracking ID that we were referring to before, so that the system will understand if you're talking about tumor X is present in multiple studies, etc. And we don't have time to go through the full set, but that gives you a good flow. In terms of the transactions, the profile is set up to use either the traditional DIMSI transactions, the CStore, the CFind, the CMove that I gather you've probably already been hearing about, as well as to use the newer DICOM web variants of the same capabilities. Key2RS for query, Wado-RS for retrieves, etc. And because these are just vanilla DICOM objects, all of the existing infrastructure works. So far we've been focused on the results generated by the AI and how the inputs from the clinical operations layer and outputs that are then returned to it are wrapped in DICOM so they can be properly managed as clinical data in the patient medical record. The AI model itself is happy just having pixel values and a list of category numbers. It doesn't really understand any of the clinical semantics of that. It doesn't care that there's a patient associated with it. In fact, it's lost track of which patient this was. Obviously, in the clinical care pathway, we can't do that. So as we feed the data in, collect the results, and bring them back out, we'll be doing mapping so that these categories then are mapped back to specific clinical semantics for influencing patient care, tied again to the patient and clinical context. And so in this first profile, we've kind of hand-waved and generalized the things going on in the clinical operations layer. So now let's look at the next profile, the AI workflow for imaging. So the job here is to coordinate execution of these AI processing tasks. So you can imagine that there's an image manager, i.e. PACS, in the department, and it's being fed a continuous stream of various types of studies. And we've gone out as a hospital and we've purchased a whole bunch of IHE of AI task performers that are capable of doing pneumothorax detections and breast tumor detections and cardiac assessments, etc. So this profile introduces the concept of a task requester to queue up the AI tasks and a task manager that help coordinate getting the appropriate task performers to work on the appropriate image sets. So the task requester might query the modality work list for current procedures, or it might listen to the image manager for image notifications, or it might be implemented as a component of one of those systems to access the information directly. IHE frequently offers, flexibility as to how the product is rolled out. What happens next, though, is that the task requester then does creation requests for various tasks, basically saying, well, this first one up there is a chest CT, and so we're going to want to run the lung nodule detection, the spinal fracture detection, et cetera, et cetera. And so it will queue up a list of tasks that need to be performed. The task manager then is responsible for communicating that information out to the task managers, as well as maintaining the current picture of what's currently underway and what's currently been performed. And so as each of the performers picks up their particular task, they interact to pull the input data from the image manager and store their results back there. Now, some AI platforms might choose to group various combinations of the image task manager, the image manager, the task performers. They might do 2 or 3, they might just do 1. There's a lot of flexibility as to how that's done, but when they are separate, how they talk to each other is defined within the profile. So the task performers in this case were shown when they're ready, they can query the manager for tasks and set a filter they know what tasks they can do, what job codes they're capable of. There would be a code, for example, to perform lung nodule detection. And they can pull down what's relevant. An alternate implementation would be for the task manager to be keeping track of all of the running task performers, find out what each of them is capable of, track whether or not they've finished their previous work and they're free now, and then assign tasks to them specifically, in which case then the performer just filters for its own ID to find out what it's supposed to work on next. So these tasks are based on a DICOM structure called a UPS work item. There's both a DIMSY version of UPS and then UPS RS with a DICOM web doing all of this with HTTP calls. It's organized into 4 attribute groups. The first section is the relationship module. Most of the AI applications probably aren't particularly going to care about this. This is mostly so that the results get fed back into the correct workflow during the reading process. This is where we have the patient demographics, the accession numbers, the admission and order details. There will be some AIs that may want to go and retrieve additional information to go with the images, and certainly this would provide them all of the links that they'd need. Here's the real piece that they'll be interested in, which is the scheduled procedure information module. So this gives them the scheduled work item code. There'll be a code saying detect pneumothorax on an x-ray. There may be processing parameters that are being passed along, maybe a sensitivity parameter or who knows, whatever it is. Those sorts of things would need to be configured in advance if they're used, but they're not fundamentally necessary. There'll be a list of input data IDs and the location. So here's the image, the identifiers. You'll have learned about SOP instance UIDs. So here's the identifiers of the exact set of images that we want you to process. And here's where you can access them. Now, the location might be a pointer to an AE title so that they can do a conventional DIMSY return, or it may be a DICOM web endpoint. And that gives you the bonus feature that if you use the /rendered version of the endpoint, the PACS essentially extracts the pixel data from the image object and returns it to you as a JPEG or a PNG, which may be a little bit quicker for the AI tool to make use of when it's doing its inferences. The parameters on the DICOM web endpoint also allow you to ask the PACS to, for example, resample the image at a smaller matrix or extract a quadrant of the image if your AI doesn't have enough nodes basically to handle full frame inputs. Some of the AIs are limited and don't want to deal with 1K by 1K images, for example. Other details would be if it's been assigned to a particular performer, that would be in the scheduled station name. There are priority flags, request completion times, and then the output destination indicates where the performer is being asked to store its results when it's finished. The progress module lets you check what state the work item in. Is it now in progress? Has it been completed? It might be canceled if there was an error. And it also includes some progress status. That was a little more for cases where you might have progress bars somewhere, or for things that take a long time to complete. It can be useful to see those, but in most cases they won't be used that much. Finally, when the performer is done with the task, it populates the output, the performed procedure information module, and it lists, here are the objects that I created, and here is where I put them. Hopefully where it was asked to put them, but if for some reason that didn't work out, at least you've got a record for where to find them. Similarly, if it needed to do slightly different parameters than it was asked for, those will be recorded in there as well. So the other aspect of the UPSRS is the notifications that we've got. We're going to postulate here that we've got, say, a watcher actor, which is part of the UPSRS framework. And maybe there's a reporting work list system out there that wants to keep tabs so that it holds off putting something on the work list until it gets the AI results back. And so it might do a global subscription to this work list, this task manager. Similarly, the requester system, when it creates each new UPS item, it could subscribe to specific UPSs. If you have multiple requesters, they may want to just keep track of their own work and not what other requesting systems are asking for. When the performer then goes and does its query and pulls back the contents and starts working, a notification gets sent out from the task manager to all of the subscribed systems, so they now know this piece of work is in progress. When it completes the work, it's then updating the content to record the objects that it's created, and then finally marks it into the complete state, which says no more new objects are going to be added, and we're done. So helpful for managing the overall workflow. In the case of the requester or perhaps the reporting work list, they could then get the contents so that they could pull this list of result instances and add those to the pool of objects that the radiologist is being asked to review, for example. So for these last two profiles, the ink is still wet in that we're finalizing the details over the next few weeks based on public comments in March. Originally, the triage aspect of AI was tucked in to the AIWI profile as a bonus feature. So this power profile has pulled that out, refined it, expanded it, and dealt with it in a little more detail. So you may have seen it before if you were involved in the RSNA AI demo. The prioritization logic can get quite sophisticated. You're trying to maximize patient outcomes, you're trying to optimize productivity of the radiologists and hospital operations, and there are a lot of interesting cases where those trade-offs come together. But the important thing that we were trying to work on in the profile, we don't define the logic the prioritizer uses, but we do go out, figure out what all the sources of information are that it would like to use, and put together the transaction so that it's getting an appropriate data feed to be able to do that analysis. And those are coming in with HL7, DICOM, etc. And so the prioritizer is attached to the reporting work list manager, and it'll use things like, the study availability. We want to make sure the study is complete before we put it on the radiologist's work list. Are the associated data available? What was the indication? We might prioritize a suspected stroke higher than something that's checking on a tube placement. What was the procedure type that was performed, whether it was a CTA versus a foot x-ray? Who is the ordering department? It's very common for anything coming in from the emergency department or the ICU to be given a higher priority than, for example, outpatient imaging. There'll be ordering provider service level agreements that may have established target turnaround times. And then this is where some of the AI results come in. If there are positive or negative findings coming in as triage signals from the AI, whether it's new or known, the prioritizer may be pulling a feed from the HIS. It's detected a potential stroke, which normally would bump that up the work list. But one of our radiologists was pointing out, if we're in, a stroke unit and the stroke was yesterday evening, we already know about the stroke. We're just doing a monitor. So the fact that the AI has triaged the presence of a stroke isn't as important a signal now as it was the first time around, unless, for example, it's in a different location. And then the tech notes is one of the areas where we're still going to be doing some work. The techs are a wonderful source of information in terms of observations of how the procedure went, how the patient was behaving. They may have gotten information from the patient that they're about to go off to see their oncologist, which means that getting this report ready soon would mean that it feeds directly into that appointment. If it's ready 3 hours later, well, it's not really going to get talked about until their next meeting with their oncologist and the like. So a lot of interesting potential logic there. The last one we're going to look at is the integrated reporting application. So previously we looked at the workflow for pre-processing with AI. This was set up to try and facilitate collaboration and data exchange between various applications during a reporting session. So there'll be your primary applications like the image display and the report creator and potentially the work list client. And then there's potentially a lot of subordinate applications. Maybe you fire up an AI tool to go do a number of measurements on this cardiac study while you're starting to work up the report. And you'd like to be able to get those measurements fed into the reporting system. So this is essentially profiling Firecast and Fire Resources and DICOM Web for allowing all of these applications to collaborate. This is actually one of the driving use cases for Firecast. So inside that hub that was in the middle, it's maintaining a data model for all of the collaborating applications. And so a session essentially represents the group of collaborating applications. So Dr. A's set of image display and report creator would be in session A, and Dr. B over at a different workstation would join session B, all being coordinated by the same hub. Within that, then, there's a report context where you have that represents a single reporting task, which is linked to an associated patient and study. And then the content is the collection of data that's been uploaded or shared by the various apps so that they can hand data back and forth. For example, to have those measurements from the AI be put in as content so that the report creator can copy paste them into the report when given a command by the radiologist. And then selections are for sharing the current focus. For if you want to click on your image display on a particular image and then dictate into your reporting system, insert link, that selection has been passed through the hub to the report creator so that it knows which image to put in, say, a DICOM web reference to. So that was a recap of 4 AI-related profiles from the IHE radiology and some of the pieces of DICOM, FHIR, and HL7 that underpin them. Keep in mind, this is a dynamic space, so I'm sure the use cases and profiles will continue to percolate and evolve, but hopefully this gives you a taste of the current state. Look forward to talking to you, from my time point next week, and we'll see what questions people have. Thanks for your attention.